Okay, now we want to take a look at the derivation of the half-life equation from the first order decay equation. First thing we need to do is simply define half-life. In the chemical process or radioactive decay process, half-life is used to define the time needed to reduce the initial concentration, whatever you choose, to 1/2 of its initial concentration. So we'll jot that down here. Half-life by definition is the time required to reduce the initial concentration to 1/2 of initial concentration. And get tight on the end there. 1/2 of the initial concentration. Okay. Looking at the diagram that I've constructed, this is, of course, the somewhat standard first order decay. We'll assume that to be a first order decay trend. And work with our definition and derivation of the half-life equation from this graph. Now, if this point represents on the y-axis 100% of the substance of interest, C, at the time equals 0, then halfway between 100 and, of course, the 0 concentration point is 50%. So what we want to do is come across the graph from the 50% point to right here, and then drop down to the time axis right here, and that's called the first half-life. Typically is abbreviated simply as T subscript 1/2 when you calculate the first half-life. Now, if we assume that this point at 50% listed here is the beginning point, then we can consider a second half-life, or the time it takes to decrease the concentration, which is now 50% of what 100% would be, to half of that number, which would be at 25%. And this would be called the second position of the second half-life. So we do the same thing from the y-axis at that particular point. We move over to the decay trend curve and then drop down to the time axis. And this point right here is the point of the second half-life. Well, one thing you need to understand about half-life times is that the first half-life time will be equal to the second half-life time, as well as the third half-life time. When we cut this one in half, I'll go ahead and draw in the position of the third half-life right here. And down here. This would be the third t to the 1/2 position right here. But the time to go from 100% to 50% is generally referred to as the first half-life. So let's set up something like this, and I know this may get kind of crowded. We'll come over here to here, and the time to go to this point from this point right here is whatever the first half-life is, t to the 1/2. Now the time it takes to go to the second half-life position is this span right here. I should have put in the line for us over here. That is your time for the first half-life. Well, this period of time from here to the 25% concentration is the second t the 1/2, or 2 first half-lives. And to go to this position from here to here, this would take 3 half-lives. But the half-life by itself is constant for a first order decay trend. But the problems will ask for what is a half-life, or how long does it take to go to the first half-life, which is what this is, or how long does it take to reduce the concentration to 12.5% remaining. Now, in working with the classic decay equation from the first order decay equation and working with the half-life equation, we have to realize that these 50% concentrations, 25, 12.5, 6.25%, make sure you refer to remaining concentrations. Some problems will be presented in the context that 75% has decayed. Okay? What is the concentration after 75% has decayed? Well, when you use the decay equation for the C sub O position, C final position, C final position, you don't put in 75%. You put in 25% remaining. So these calculations refer, while this is not dependent on concentration, you'll see this in a moment. The reference is to, of course, the remaining concentration, not how much has been consumed. Okay, we can continue to the fourth half-life out here. If we wanted to draw a fourth line, I'll try to be as neat as possible for your reference as I can. Let's do it here. Looks like that's going to be going to hit right about here, my guess. So we'll draw our line from there to here, and then drop down to the time axis right there, and that position is the fourth half-life. The time it takes to decrease from the initial concentration of 100% to a position of where 6.25% remains is this period of time. So that would go through 4 times t to the 1/2 there. But keep in mind, the half-life, when calculated for the first order decay equation in this trend, is constant. The first half-life time is the same as the second half-life time, this period in here. The period in the third half-life time is the same as the first half-life. The third half-life time is the same as the first half-life time, and the fourth half-life time, of course, is the same as all of the other half-life times. So one of the purpose of this is to give a practical description of what we're talking about in terms of half-life as given. Now, the issue is, what is the half-life equation, and how do we get it from the first order decay equation? Well, if we're using the terminology of C for reactant concentration, then we'll simply say the concentration at some time t in the future, or final concentration, is equal to the initial concentration, e to the minus kt, where k is the rate constant and t is the time of interest, right here. Now, in substituting the final concentration here as the position of the half-life, or when half of it, of C sub O, is been consumed, if you will, or half remains, then we take C sub O divided by 2. So C final is now C sub O over 2. That's the final concentration, half of the initial concentration. Right there, E minus KT. And when we substitute that, we now embellish the equation with a subscript of 1/2 on the time term, right here. This up a little bit. It's like that. So if I divide both sides of this expression by C sub O, whatever it is, then I have 1/2 equals e to the minus kt. Well, the equation can be simplified by turning it over. You can divide both sides by or convert both sides to positives right here, so that we can get in a more useful form. I can turn that over to, see, this is actually a reciprocal. I can draw that in, 1 over e to the plus kt, like that. Well, we want to untangle the reciprocal, if you will, and so this would then be 2 to equal e to the kt, and that would be 1/2 power. If I take the logarithm, natural log of both sides, or ln of 2 equals the ln of e to the kt to the 1/2, like that, I will obtain ln of 2 is 0.693 to equal kt to the 1/2. This is the half-life equation, as is generally called, right there. So you'll have problems to work and using the half-life equation. Here are several problem types that you'll run into when working half-life and decay excuse me, decay equation type problems. As the problem is presented, you'll see data come in various forms. Calculate a final concentration time t given the K value, the rate constant, and an initial concentration. And you would simply substitute into the decay equation and calculate C final. Or you might calculate the initial concentration, where you're measuring a concentration today or at some future time. Okay? So you would calculate the initial concentration at 0, given at time equals 0, given K and T, and of course the current time. I inserted the current time, and this of course refers to the time to achieve final concentration. Something like calculate the initial concentration of C if the concentration now is such and such molarity at 50 seconds, and the rate constant is given to be such and such. So you would need the time for the final concentration. Another problem is calculate the time required to reduce a concentration from initial concentration to a specified concentration, simply given the value of K. And so you have to deal with the T expression, solving that. It's a very easy approach in terms of calculating the T value there. I'll show you in a moment. Calculate the final concentration time T given the initial concentration and half-life. Well, here is a two-part problem. One, calculate K from the half-life value using the given CO T to 1/2 and the K value. You'll have to have the K value also. Okay, you apply that. You'd have the K value, sorry. That's the objective. a two-part problem, calculate K from the half-life and then apply this K value to a decay equation to determine CF and C final. Brain's running away with me. Calculate final concentration time TF given C sub O CF at a time different from TF of interest. This too is a two-part problem where you calculate K from the decay expression, decay equation, and then you apply the K value to the decay equation again to get the CF at the new time. So you will have a T1 and then you'll have a T2. And here the T2 is the ultimate answer to the problem. So we'll take a look at these right now and see what the procedures would be. Okay, here is a problem that illustrates the issue in case 1 problem types. I'll put up here case 1 problem types. So go back to the list and you might check that out. But anyway, here is a cyclopropane heated at 500 degrees will produce an isomer of polypropylene shown here. It's a vinyl structure which can be polymerized through this double bond, but anyway, producing polypropylene. Forming the monomer, 1 unit, the isomer monomer of polypropylene is a first order process. Also given in the problem is your K value, which is 6 times 10 to the minus 4 per second at 500 degrees Celsius, and the initial concentration of the cyclopropane to be 0.0226 mole per liter. The question is, right here, what is the cyclopropane concentration after 899 seconds? So this is straightforward in terms of applying the data to the first order decay equation. So we start with C equals C sub O E to the minus KT, and the problem is asking for the final concentration. Now what I recommend is simply substitute the givens into this equation and solve on the calculator. Now some will problem solutions will come up and show converting that back, the equation back to logarithmic form. Well, that's fine, it gives the same answer, but I'm going to show you how to just substitute straight into the equation and calculate the concentration. Okay, the initial concentration is 0.0226 mole per liter is molar. I'm just going to put capital M. And then we want E to the minus KT. Now what I recommend is a minus bracket, and K is 6.0 times 10 to the minus 4 per second times 899 seconds, and bracket that off. This allows you to cancel the time units in that part of the equation, and it also says calculate what's in the brackets first and then apply the negative sign. So what it just avoids, in my opinion, miscalculating the E function here. So this would show, this would give this times this is 0.5394. So now you have e to the minus 0.5394. Then applying this to the calculator, now I use this TI-30X right here, and we'll just show you how that fits in. I enter 0.5394, and apply a negative to this, and I need the second function here, e to the x, so I hit second e to the x, and this is e to the minus 0.5394. So I will substitute that into my calculation, 0.0226 molar times 0.583. I'm going to round it to 4 significant figures for the moment. Now the final answer will be in terms of the data generated here, which will be 3 significant figures. We'll see that in a moment. Okay, this is your reduction factor. The exponential form right here gives you a fraction of the original concentration, and so this number times 0.0226 is now times 0.0226.5831 equals, okay, so we are at 0.0131786 molar. In other words, cut it in about half the original concentration. Now, this is a calculator answer. And the more appropriate form would be to select the number with the least number of significant figures and the multiplication. So the 226 would be the significant figures in the data, and so we would round this to 1, 2, 3, 7 would make that a 2. So I would express the final answer in this form, molar. Okay. Okay, now let's take a look at case 2. Calculate the initial concentration given a specified concentration after a period of time and K value also given. Okay, so here's your problem. Calculate C sub O for the following reaction if current measured concentration is 0.00067 molar after 155 seconds. The reaction is first order with a rate constant of 2.58 times 10 to the minus 3 seconds to the minus 1. like that. So using the decay equation, C equals C sub O e to the minus kt. Our objective, of course, is the C sub O. What I'll do is I'm going to substitute, and of course you can go ahead and solve this for C over e to the minus kt, substitute your numbers, and then come out with C sub O. I'm going to set it up here first. So the current concentration of interest is 0.00067 molar, and so that would be this term, and we're interested in finding C sub O, so I'm going to bracket off the e to the minus k, which is 2.58 times 10 to the minus 3 seconds to the minus 1 times the 155 seconds. This gives us an expression to equal solving for the initial concentration. The computation goes to 0.00067 divided by 0.67. Comes out in moles per liter, which ultimately comes out 0.00100 molar, or 1.00 times 10 to the minus 3 molar. Okay, case 3, calculate time required to reduce an initial concentration C sub O to a final concentration CF given K value. Okay, look at this problem here. Let's calculate time required to reduce concentration of N2O5 gas from an initial concentration of 0.015 mole per liter to 0.005 mole per liter. The reaction is first order decay and N2O5 with a K value of 6.2 times 10 to the minus 4 reciprocal minutes. Now, in this case, we want to use the decay equation with the objective of obtaining T. In this case, you will need to solve for T, you'll need to convert this back to natural log form. We'll go first to C over C sub O to equal E to the minus KT. Now, we take the logarithm of both sides to equal ln of E to the minus KT, and E to the minus KT is a minus KT. So taking this term and this term together, we wind up with ln of C over C sub O to equal minus KT. Now, some problems will require you to calculate T given C, C sub O, and T. You calculate K. Or in this case of this problem, we want to calculate T. So just as a matter of interest in passing, this can be solved for a K value if the data so dictates, and that would be ln of C over C sub O over a minus T. This will be a fraction, and when you take the natural log of that fraction, it'll be negative. Or this expression can be solved for the time it takes to change the concentration, which is of the same form, except you're dividing by a negative value of the K constant, like that. And this, of course, is the objective of the problem we are working with. So using the first order decay equation, we can get it into a form ln of C over C sub O over K. This is classic. Move that up a little bit. So using this expression right here, we'll go T equals ln of C over C sub O divided by a minus K. And then we'll put ln of the final concentration, 0.005 molar over 0.015 molar. Well, I might as well put them in, cancel them out, divided by a minus 6.2 times 10 to the minus 4 minutes to the minus 1, like that. So the time will come out in minutes in the given problem. If you want it in seconds or hours, convert certainly after the fact. So the ln of 0.005 over 0.015 is equal to a minus 1.098612 by the calculator, divided by a minus 6.2 times 10 to the minus 4, and this will be in minutes. And this ultimately is shown to be, I'll tell you what, I'm going to move this down to here so I can illustrate the rounding to the significant figures. 1771.955,304 minutes. Well, in computations like this, and I should put 50 right there, and 50 just to keep it consistent. I want this in 2 sig figs. So from the data here and here, we count left to right, 1, 2 significant figures here, and that 0 after the leading 5 digit is also significant figure. So we have 2 significant figures. So this needs to be rounded to 2 significant figures. So this would then be rounded to 1800 minutes required to reduce the concentration from 0.015 to 0.005. Okay, let's look at this problem. This case scenario is calculate the final concentration, giving you an initial concentration of a component and the half-life of the process. Okay, here's a problem that deals with case 4 of the reaction types or decay problem types. The decomposition of azomethane is given by this equation. Here's structural formula for azomethane producing ethane and molecular nitrogen. If in an experiment the initial concentration is given to be 1.13 times 10 to the minus 2 mole per liter or molar, what's the concentration after 2 hours? And you're given a half-life. Well, the process of solving this one requires, of course, using the C equal C sub O e to the minus KT. Well, there are two issues here. One, you need to calculate the value for the rate constant, and two, you need to convert the value given for time into seconds. So we're given it in 2 hours, and we'll need to convert it to seconds. So from KT to the 1/2 equals K times T, 1/2 equals 0.693. You can solve for the rate constant to be 0.693 over T to the 1/2, which is 0.693 over the half-life, given right here 2.79 times 10 to the 3rd, and that's going to be in seconds to the minus 1. The K value is 2.48 times 10 to the minus 4 reciprocal seconds. The value for time of interest is given as 2 hours. So if time is in 2.0 hours, say, you need to convert the hours to match the units of the rate constant. So we'll multiply the hours times the conversion factor of 3,600 seconds per hour to equal 7,200 seconds. Right there. Now we're given the initial concentration to equal 1.13 times 10 to the minus 2 mole per liter. Like that. So now we substitute into the decay equation, and we can calculate C final. It equals 1.13 times 10 to the minus 2 molar, and that'll go E to the minus K value 2.48 times 10 to the minus 4 seconds to the minus 1 times the 7,200 seconds, like that. Use up just a fraction or two. Then this will give us 1.13 times 10 to the minus 2 mole per liter, and the E to the minus KT calculates to be 0.168. So the initial concentration will be decreased to 0.168 of its original amount, and that comes out to be 1.90, 3 significant figures, times 10 to the minus 3 mole per liter. Okay, the last case of interest is, say we're given an initial concentration and a final concentration, and we know how long it takes, or that's given, C1, how long it takes to get from CO to C final 1. The calculation is calculate a second concentration at a time T2, certainly greater than T1. Now, here's an example. The reaction of chrome ions plus thiocyanate ions produces the chrome thiocyanate complex as shown here. It is first order in the chrome ions. If in an experiment it was determined that a 0.108 molar aqueous solution of chrome 3 ions in an excess of thiocyanate ions decreased to 0.054 molar chrome ions in 5.8 hours, how long would it take for the concentration of chrome ions to decrease to 0.027 molar? Well, this would be, and again, another time calculation that would be derived from the decay equation. That is C final equals C sub O e to the minus KT, and as shown earlier, this can be rearranged and expressed in a time relationship or K relationship. We need to calculate K in this problem and then apply it to the second concentration, and K is ln of C over C sub O, C final over C sub O over a minus time. Okay, so the K value is now ln of C final and C initial from the first experiment. So the first experiment showed a final concentration of 0.054 molar. 0.054 molar, starting with a 0.180 molar, and this decay took place in 5.8 hours. Now, the calculation can be completed in terms of hours. Most researchers will do the seconds thing. I'm going to convert this to seconds just for interest. And molarities drop out, so I'll just not put that in. And that's divided by, should be a negative there, a minus 5.8 hours times 3,600 seconds in 1 hour. Now, this works out to be, for the ln of 0.054 over 0.180 to be a negative 0.6932. Now, that's then divided by the product of 5.8 and 3,600, which comes out 20,880 seconds. And when applied to this expression, comes out seconds to the minus 1. Therefore, K is now equal to, working this out, 3.32 times 10 to the minus 5 reciprocal seconds. Now we can apply this into the decay equation. to calculate how long, T2, it would take to achieve a CF2, or a second final concentration. So what we'll do is we'll set this up as a C final 2 to equal C sub O e to the minus k T2, and T2 is now equal to ln that's C final, not CO. C final 2 divided by C sub O, and that is divided by A minus K. Okay, so substituting values from the problem into this expression, we find that T2 is equal to ln of C final 2, which is 0.27, sorry. And we can continue to use the 0.108 molar, and that format about K, I'm looking at K value, there it is, K value of 3.32 times 10 to the minus 5, right there. And this now comes out in seconds when you complete the calculation. So this now comes out as a, hope I can keep from making this too crowded, minus 1.3863 over a minus 3.32 times 10 to the minus 5, and that's in seconds, which turns out to be 41,756 seconds, or in hours, equals 41,756 divided by 3,600 hours, which equals about 11.6 hours. Okay, that completes the background and examples on the decay equation and half-life.